In a few of my previous videos, I talked about how multimodal sensor combinations, which include radar, are more suitable for complex road environments than a vision-only approach in autonomous driving technology. However, someone pointed out, "You're still saying multimodal sensors are better than pure vision?" This made me realize that the information I had was outdated. So why are so many people now saying that pure vision is superior to radar? The turning point came earlier this year when Tesla released FSD, Full Self-Driving V12. To explain this shift, I did some research to break down the principles of autonomous driving technology. And here's what I found. Tesla's CEO, Elon Musk, mentioned back in 2022 that if Tesla fails to achieve full self-driving, the company will be worth nothing.
Overwhelming focus is solving full self-driving. And that's essential. And that's really the difference between Tesla being worth a lot of money and being worth basically zero.
This highlights how crucial autonomous driving technology is for automakers to survive in the future market. Currently, there are two main approaches to perception technology in autonomous driving. One is vision-based technology, where the system relies solely on cameras. The other is sensor fusion, often referred to as radar technology, which involves a combination of sensors, including cameras, radar, and LiDAR. Most smart car companies today opt for multimodal sensors with radar to enable advanced driving assistance features, but Tesla stands out by choosing the less common approach, using cameras without radar to gather environmental data. While there have been reports that Tesla added millimeter wave radar to some high-end models, Tesla remains a champion of pure vision technology. To give some background on radar, the first self-driving car to use LiDAR was Google's Waymo. Google began developing self-driving technology in 2009 and was the first to apply LiDAR to test vehicles. Today, Waymo has achieved Level 4 autonomy and is already offering commercial autonomous taxi services in some US cities. You can clearly see the 360-degree LiDAR on top of Waymo in videos. In my previous videos, I often mentioned that multimodal sensor fusion or radar technology was more suited to complex road environments. This conclusion was based on the algorithms used by most car companies at the time. However, with Tesla's new V12 using an end-to-end algorithm, the balance has shifted. Many now believe that the highest level of autonomy, Level 5, which was once seen as unattainable, can now be achieved using pure vision technology. In other words, pure vision technology may now outperform radar. Let's try to explain why. When Tesla released FSD V12, it significantly outperformed the earlier V11 version in various tests. Some even tested the V12 version in the busy streets of New York's Times Square, where the car handled chaotic traffic and pedestrians with ease, operating more like a human driver than V11. So what led to this breakthrough? The key is Tesla's new end-to-end algorithm, which replaces the older BEV plus transformer framework. Let's call the latter the traditional algorithm. The BEV plus transformer framework was originally introduced by Tesla and is now used by many automakers. It sounds complex, but it essentially involves two main technologies: bird's eye view, BEV, and the transformer deep learning model. If you've seen our previous videos, you'll know that transformer is currently the most popular algorithm in large language models. We don't need to dive too deeply into these technologies, but to understand the traditional framework, here's a brief overview of its process and why it theoretically cannot achieve the ultimate goal: Level 5 full self-driving, where no human intervention is needed. This is because the traditional autonomous driving algorithm is modular. It processes data from perception to decision-making to execution. The car's sensors, like cameras and radar, collect real-world data, which is then processed by the perception module. This module extracts key information and sends it to the decision-making module, which matches it with preset strategies. And finally, the car performs the corresponding action. Here's something important to note. The perception module only sends certain data to the decision-making module data deemed relevant to driving, like pedestrians or other vehicles. Data considered irrelevant or rarely encountered during training is ignored. For instance, if a weasel suddenly appears on the road, the perception module might not recognize it, leading to no action being taken. Likewise, details like the color of a car or whether it's signaling might be ignored if developers deem them unimportant. This is crucial for understanding the overall issue. The perception module only identifies a portion of the road information, not all of it. This selective processing can lead to problems when important data is missed. Now let's talk about the decision-making module. This module acts like the command center of the autonomous driving system, deciding how the car should act based on the dynamic data provided by the perception module. For example, stopping at a red light or steering around a pothole. The decision-making module relies heavily on rules and logic set by developers. The challenge is the complexity of the model. For instance, at an intersection with dozens of moving objects, the different combinations of objects with different speeds and directions could lead to thousands of scenarios, resulting in complex and lengthy code. In reality, it's impossible to account for every possible scenario, so these preset rules are limited, and some real-world situations can't be anticipated. Can you see the issue now? Because of the characteristics of the perception and decision-making modules, traditional algorithm can't handle all driving scenarios. Developers can add new objects or details to detect, or create new decision-making rules, what we call patching, or upgrading. But no matter how much you improve it, all system processing is based on preset rules. The real world is too complex and unpredictable, and when something unexpected happens, the car won't know what to do. This is why in some autonomous driving situations, the car just stops, or worse, causes an accident. So, the drawbacks of the traditional algorithm suggest that it may never achieve true Level 5 autonomy. However, the end-to-end pure vision approach solves these issues. In fact, it's the first algorithm that truly integrates artificial intelligence into autonomous driving. Let's look at how this framework addresses the problems of the traditional architecture. Tesla's end-to-end autonomous driving is built on the end-to-end neural net. In this framework, all the data from Tesla's 8 cameras is fed into the neural network. There are no preset rules. Instead, the machine learns to analyze and summarize the data itself. It learns what actions human drivers take in various situations, or to say image pixel patterns, figuring out why a driver would brake or make a U-turn in certain scenarios. The video feeds from the 8 cameras are broken down into the smallest pixel units, and AI performs deep learning on a massive amount of raw data. This means that instead of developers telling the car how to drive by hard-coding specific rules, the AI-powered car learns to drive by observing and mimicking human drivers through extensive training. You should understand that the memory and processing power of AI is far greater than that of any individual or group of people. Tesla's AI is powered by Dojo, a supercomputer specifically built to train the FSD neural network. The supercomputer's powerful learning capabilities can discover correlations between image pixels and driving actions far beyond what humans can summarize. Of course, this requires massive amounts of training data. It's said that Tesla's FSD V12 was trained on video data from millions of Teslas around the world, simulating human driving decisions. So, unlike the traditional algorithm, where the perception module filters and discards some environmental data, the end-to-end process treats everything as a whole. All data is preserved and the entire real-world environment is considered in decision-making. Every smallest unit of data is fed into the system, which directly outputs control decisions. The whole system is a neural network, and there's no need for developers to hard-code rules line by line. This is what Elon Musk means by photon in, controls out. Recently, after visiting the US, He Xiaopeng, the CEO of XPeng Motors, another famous New Force automaker, announced that their upcoming new model will ditch LiDAR and adopt a vision-only approach similar to Tesla's. Keep in mind, XPeng was the first automaker in the world to install LiDAR in mass-produced cars. It seems that the smart driving industry is once again following Tesla's lead. In summary, under the traditional autonomous driving architecture, radar seemed to be the fastest shortcut to achieving self-driving to some extent. However, with the added power of AI and computing, pure vision technology is making a comeback and is now seen as the most promising path to achieving full self-driving. This shows that many so-called conclusions are relative over time and can't be set in stone. But one thing is certain: we're getting closer and closer to truly autonomous driving without human intervention. Okay, thanks for watching. See you around.